Even the most ingenious mechanism consists of the fundamental joints and links. Actuate the joints and the whole mechanism will reconfigure. Traditionally, the robot is fully actuated, which means there is a numerical balance between the degree of freedom and the numbers of actuators. But it brings a paradox. A higher degree of freedom gives more flexible configurations, but it also demands more actuators. Which is bad, because it always follows by the heavy consumption of energy, the complexity of controlling system and more physical occupancy. Here is a case of Kirigami surface to illustrate it. Actuating each gray subfold, it is able to transform into multiple three-dimensional surfaces from the original flat sheet. It is very useful to enable morphing phased array antennas of tunable properties through geometric changes. But the DOF of this design has reached up to 84. It means there have to be equal folding actuators to make all the reconfiguration happen, which is nearly impossible for the practical applications of aerospace. Multistability brings an effective solution. Let's imagine this: if you want to move a ball to two appointed locations, you have to bother two actuators with two independent directions and use them perfectly to relocate the ball. It is exhausting to just depict it. But if we could somehow set up a landscape and bring everything into a three-dimensional space, the ball would automatically fall from one local minimum point to another, even after a single simple and inaccurate actuator for a short period of time. That is exactly what the multistability works here. Energy is introduced to form an energy landscape. And every point in this configuration space represents a unique configuration. The points at the local minimum of the energy landscape are thus the stable configurations. The shift of the ball, which is also the reconfiguration between these stable states, would be easy and impulsive due to the nearby attraction domain. The derived self-lock property would preserve its geometric configuration after a slight disturbance. Many multistable structures of surfaces, robots, and emergency supplies have been made to illustrate the merits of fewer actuators to achieve multiple stiffened configurations. In this paper, we propose a multistability design framework for spatial linkages, which is a fundamental building block for mechanical designs, and aim to help avoid the high DOF problem. Let's say we have an arbitrary 4 linkage. So generally, it is immovable or monocompatible, and has to be stable at the current state. However, if we add some particular constraints to regulate its structural parameters, it would transform into an overconstrained mechanism with an additional degree of freedom, which is continuously compatible along the reconfiguration. In other words, these structural constraints make the monocompatible linkage to be a continuous compatible one. What if the compatibility is merely imposed on certain discrete configurations? It then turns into a multistable structure being stable at these states. And there would be a more flexible design space because of the relaxed requirement of compatibility. So how to implement it? The first thing is to parameterize the spatial linkage with the DH notation. And if we look again to the constraints with this language, we find they all come from the closure condition of closed-loop linkages, which, if violated, it cannot come back at the same beginning points, and naturally the linkage would be open loop. And when the closure condition holds for all configurations with rotational angle, theta, it is the continuous compatible mechanism. So decrease it down. Let it hold only for the finite states where we want the linkage to be stable. And the multi-compatibility is established there discretely. Here we show a bistable for a linkage. The linkage is 3D printed with two materials, where the dark links are made of the carbon fiber, and the white hinge joints are made of the TPU. With a simple linear actuation, it can switch to another configuration impulsively, or switch back. The pull force along the reconfiguration indicates the resistance of the structural deformation when switching from stable states. If assuming all parts of the linkage are deformable, the reconfiguring simulation with truss model gives an evaluation of the strain explicitly. But physically, the elastic deformation of joints contributes to the most part of the energy barrier because of the wide difference in Young's modulus between two materials. Now we acknowledge the potential of an overconstrained mechanism being changed to a multistable structure. We even managed to get a tristable linkage from a Bricard mechanism. So the next question is how to appoint the stable state to the configuration where we want. We actually set up a standard constrained optimization solver for the inverse design. Let's start from the beginning. Few things need to be determined in advance: the formation of the linkage, and the approach of the appointment. Let's just say you would like to have a 4R linkage with the stable states at 0 degrees and 180 degrees. Which suggests you use the angle to express the target configurations. But you can always turn to another approach, like the arc length or the enclosed area. Then, we need to translate the needs with the DH notation for linkages. The DH notation is just an option. It is still feasible for other mathematical notations, as long as the closure constraints can be explicitly expressed. Now, we can identify all the designable parameters in the design space. Then we are ready to go to the next computing module to get an initial guess. You might pick the initial guess randomly. But out of the consideration of computing efficiency, it is highly recommended to get an overconstrained mechanism of the same formation as the guess. Besides, we hope the motion curve of this mechanism can pass through all the target configurations as much as possible, such that it can be closed to the final multistable structure at the largest extent, which is good for rapid convergence. So again, a standard constrained optimization solver, but a minor one. The objective function is set as the accessibility of the target. And the nonlinear constraints are set as the structural conditions of overconstrained mechanisms. The initial guess for this minor solver can be picked randomly. As a consequence, some computing loops are involved to guarantee the final output of it is converged. At this point, we can hopefully have an appropriate initial guess. And we are going to enter the major constrained optimization solver. The objective function is set to maximize the overall stiffness at all stable states, in case it turns out to be a pseudo-mechanism. As for the nonlinear constraint, it consists of several parts. Essentially, the compatibility condition is aimed to impose the closure equations on the prescribed target states. The accessibility condition defines the threshold of the difference between the result and the target. No self-interfering condition makes the final result work physically well. You can always add some other constraints based on the needs. Size, orientation, anything. But just be careful not being too strict to output a feasible result. This optimization problem is then fed to the MATLAB Lincoln function and solved to get a single loop MSSL. Now as the next step, we are trying to assemble them for more complex target configurations. The first and instinct construction is stacking. To ensure the assembly is still a multistable structure, no additional degree of freedom is introduced. So the coupling strategy here is fixed with rigid frames. Then these two pairs of leaves will rotate together and thus the hinge joints are coupled well. Mathematically, it is put as a coupling condition. Thus, a reconfigurable tube has been built. In this way, as the actuation is imposed on any of the modules, the overall transition would be triggered. In fact, it is not necessary for the coupled MSSL modules to be identical or aligned perfectly, as long as the variation of their rotation angles is equal. It is actually better when aligning at a certain shift angle gamma, which can help to construct the tube with customized hollow rate for the benefit of medical stents. To simplify the analysis, here is a case of two identical modules. Its projected area is equivalent to a quadrilateral enclosed by the middle points of the hinges. Because of the coupling conditions of the modules and the coupling frames between them, the projection will change simultaneously. Thus, the intersection area and the union area of the tube varies respectively. and so as the hollow rate does. In summary, the stacking coupling of MSSL modules can form reconfigurable tubes with a customized hollow rate, which play a similar role as throttle valves in the vessel to regulate the fluid capacity as needed, when or after the deployment. The next coupling approach is chaining. Similar to the stacking coupling, the coupled hinges are fixed with coupling frames to decrease the additional degree of freedom, while the coupling conditions turn to an inversed form. Thus, the reconfiguration can be transmitted through the coupled hinges. In this section, we are inspired by flytraps and propose an impulsive gripper with 2 identical MSSL modules and 1 Bennett linkage. There are 2 obvious advantages of this design. 1, able to generate a symmetric clamping action because of the same MSSL modules at the end, and 2, easy to be overall actuated because of the continuous kinematic transition of the overconstrained mechanism at the center. Physically, to decrease the overall complexity of the design, the coupling hinges of 2 adjacent modules are simplified and merged as a single hinge when assembling. The experiment validates that, even with such a compact design, the 3-module gripper exhibits an impulsive behavior in less than 0.4 seconds. The slow-mo further indicates that this impulsivity is brought by the rigid and non-rigid deformation of each module. After this, the gripper is able to recover to the standby state gradually, exactly as flytraps do. Now we are trying to design its clamping ability. One direct way is to turn back to redesigning the MSSL modules with different configurations. What is more convenient is to keep them but simply change their installation parameters. Thanks to the continuous kinematic curve of the Bennett linkage, it is able to be structurally compatible with the coupled MSSL modules at a wide range. It thus gives us some extra design space of clamping range. Here we are showing 2 examples with the different initial coupling angles to analyze its influence. A similar uprising trend is observed before the range reaches the peak respectively, and then they would experience a rapid decline. It is noted that the maximum clamping range is increased with the initial angle. More improvement will be discovered if we decide to design the Bennett linkage more detailedly. When the twist angles of the axis, alpha, and beta, change, the maximum clamping range would be affected as the figure indicates. So, it is all about this work. More details can be found in the text content. Briefly, we revealed the potential of all types of overconstrained mechanisms being transformed into multistable structures, and supported it with several representative cases. They might be a little naive and rough for practical uses, as lots of actual constraints are ignored. That is exactly the reason we made this video, to welcome whoever puts this technique forward to your expertise, rather than let it stay as a good but conceptual idea.